Welcome to the next video in the real analysis video series, and we are going to move on to another proof. So we are going to claim that the additive inverse, right? You can't yet read these things the way you're kind of used to from high school algebra. You have to read that as the additive inverse of x. What we are going to prove here is that you get the additive inverse if you start from x and multiply by -1, right? Feels so familiar and obvious that you might be surprised that it is even possible to prove these kinds of things. But they really mean different things, right? That is the additive inverse of x, and this is a product of some two numbers, so they really do mean different things. And we are going to prove that, in fact, you get the same thing from these two different concepts, I guess. Okay, anyway, in order to prove, think about the fact that we've already proved that additive inverses are unique. So we know that the only thing that is an additive inverse of x is -x. So if we can show that -1 times x is an additive inverse of x, then the proof will be complete. So let's do that, right? Let's try to show that -1 times x, if you add it to x, the result is 0. That'll show that it's an additive inverse, and since we know that this is the only additive inverse, then it must mean that this equals this. Okay, that's the game plan. So how do we do it? Okay, we're going to take these two things, add them together, try to show that the result is 0. We've got two things added together. They've both got an x in them. That sounds like we could factor out x. Wait, but we're not allowed to use concepts like factoring out because, right, we're supposed to be sticking to either the axioms or the things we've already proved. Oh, but wait. We have that distribution law, and actually factoring is just using distribution in reverse. So actually, the thing that we called distribution, right, the fact that multiplication distributes over addition, could just as well have been called the fact that, real numbers can factor out of sums, right? They're just the same thing but just one is applied in one direction, right? When you take a multiplication on the outside and distribute it inside, that's distribution. But if you just run the exact same equality in reverse, right? The equality doesn't care about the direction. So it's just viewing the same thing, but going in the other direction. That's the same thing as distribution. So anyway, I guess long story short, man, that was a lot of talking just to tell you that it is completely valid by the axiom of distribution that, in fact, we can factor out x. Now, to be really explicit about factoring out x, we really should write this as 1 times x so that we have like a number here, both of them have x on them, and then the axiom of distribution really lines up with when it is written this way. So we write it with this extra factor of 1 so that it becomes really explicit and clear how we are using distribution or, factoring. And now we can factor, right? So we pull the x out, and there's this left on the inside. But then we know that that's 1 minus 1, and anything minus itself is 0, and therefore this is x times 0. And we have proved just a moment ago that that is the same thing as 0. So halmos. Okay. On to the next theorem, that negatives cancel, right? That -1 times -x, or -1 times the additive inverse of x, if you want to be very technical, results in x, as we kind of already know that it does, but that's we got to prove all these things. And then the book also claims that -x times -x is the same as x squared, which is to say just x times x. We are going to go ahead and temporarily understand that x to the n is the same thing as x times itself n times, no matter what natural number n we choose. But I'm going to go ahead and omit the proof. I think the book is probably pretty clear. I'm sure I have my reasons for omitting the proof. Probably I just want to go fast. So, okay. Let's move on. And so we get this trichotomy of order. So this says And notice, by the way, that when we write x is strictly less than y, what that really means is that x is less than or equal to y, right? Because this is the officially defined thing, right? That was the thing in the axioms. This is unofficial, but we're going to go ahead and use it and just understand that what it really means in the, right, like we can kind of exchange it for the official language anytime we want, and what it officially means is this right here, which I think makes intuitive sense. So good, let's move on. So the law of trichotomy says that if you do strict, x strictly less than y, that's possible, or they're equal, or x is bigger. But the kind of, the thing that makes this a trichotomy rather than just three different possibilities is that if any one of these holds, then the others must not. So this is all encapsulated by saying that precisely one of the three holds, right? So one of them must hold, and if it holds, none of the others does. Okay, let's prove it. To begin with, let's show that at least one of the three must hold. So by the order axioms, right, the fact that it's a linear order tells us, and I think what this is, like the comparability axiom or property or whatever that says that for any two things, they are comparable. Either x is less than or equal to y, or y is less than or equal to x. So that's like the commensurability fact about the order, a linear order. And so, okay, so we know that this must be true. And then, right, we're trying to prove that one of the three cases listed earlier must hold. Without loss of generality, let's assume the former. And in that case, let's further subdivide the cases into the possibility that x is equal to y or x is not equal to y. One of those must hold, somewhat obviously, and if the former holds, we are done, right? Because that was one of the three things that we were trying to show, like that. So if that holds, then one of the three things holds, okay? But what about the other one? What if x is not equal to y? And we are assuming, remember, without loss of generality, we are assuming that x is less than or equal to y. We're now assuming further that x is not equal to y. Well, by definition, that must mean that x is less than y. And again, that now shows that, yep, in either of these two cases, right now we've shown that this holds. So, yet again, no matter which way you go, one of the three things in the trichotomy must hold. Okay, that'll conclude the proof that at least one of the three must hold. We now have to proceed to show that if one of them holds, the other two do not. Okay, just let's pick somewhat arbitrarily and assume that x is less than y. Let's assume that that holds and show that the other two must not hold. Well, by definition, what it means for x to be strictly less than y is that x is less than or equal to y and that they are not equal. Well, that already, right, this right here shows that the middle one, x equal to y, does not hold in this case, right? So because of this assumption, that equality does not hold. How do we get the remaining one? Does newt hold, does not hold. Okay. Moreover, we know that the linear order says that if x is less than or equal to y and y is less than or equal to x, right, if those were both true, right, because, keep in mind what I'm trying to argue at this moment is that this cannot be true. So let's just imagine briefly that it were true. If it were true, then you'd have both of these. And we know by the order axiom that then that would mean that x and y have to be equal. But we know, right, we already, right, that we're in, this whole portion of the proof is assuming this right here, which gave us already that they are not equal. So that can't happen, right? So basically what I am arguing is that this cannot be true, right? That if you assume this, then you cannot have this, because if you did, you'd reach a contradiction, right? You'd have that x is equal to y, but also x is not equal to y. So it can't happen. And therefore, since that is not true, then therefore y strictly less than x also cannot possibly be true. Because that's part of, right? Like part of this is this. So anyway, I hope that's clear. So I have now shown that if x is strictly less than y, then none of the other two cases in the trichotomy holds, and I claim that the remaining cases are either easy or they are proved similarly, so I write the Halmos. Let's keep going, right? That might have been a long, right? This might already be a somewhat long video, but let's just keep going. So, because there's just a bunch of theorems. Maybe I won't even prove this one. Probably I'll only prove one of these. So anyway, let's do these order arithmetic theorems, right? So if x is less than y, then adding z preserves the order. We already saw a preserve the order fact, right? That was actually one of the axioms, but this one is stated for strict less than. So, it's all tedious. We know that it's going to work out, but the point is to get some exercise in doing proofs and also confirming every little thing. So, okay, let's, at the very least, let's get some exercise doing these kinds of proofs. So, which one am I going to prove? The textbook proves the first one, so I'll prove the second one, and, between me and the textbook, we'll leave the remaining for the viewer as an exercise. So, okay, let's take that 0 is less than x implies that negative x is less than 0. It's a pretty straightforward proof. If 0 is less than x, then we're gonna solve this with the assumption that the earlier thing has already been proved, and therefore I get to use it, right? So I'm gonna use the earlier fact to prove this fact, and so from here I can go ahead and add negative x to both sides, or subtract x from both sides. So then I get, from the principle of the earlier part of this theorem, that 0 minus x is less than x minus x, but we know that 0 plus anything is 0, or in particular this simplifies to negative x, and this simplifies to 0, and we're done. So that is basically the proof. Okay, yeah, Halmos. Okay. Well, maybe that's long enough for a video, so let's end it here. We'll pick it back up in the next video.